Welcome! In this session, we will explore an interesting coding problem titled Number 1868 Product of Two Run-Length Encoded Arrays. We'll break down the problem, discuss potential approaches, and analyze the solution step by step. Let's dive in and start solving. In this problem, we are working with run-length encoded arrays. These are arrays where each element is represented as a pair. The first number in the pair is the value, and the second number is the frequency, or how many times that value appears consecutively. For example, instead of explicitly listing 1, 1, 2, 2, 2, 3, we represent this as 1, 2, 2, 3, 3, 1, which captures the same information in a more compact form. The task is to compute the element-wise product of two such encoded arrays. This means multiplying corresponding elements from the expanded versions of the arrays and returning the result in a similarly encoded format. The input consists of two lists of these encoded pairs, and the output should also be a run-length encoded array, representing the product. Let's take a look at the input and output formats to get a clearer understanding. Here's the first example to illustrate the problem. We are given two encoded arrays, encoded 1 as 1, 3, 2, 3, and encoded 2 as 6, 3, 3, 3. When we expand these, encoded 1 becomes 1, 1, 1, 2, 2, 2, and encoded 2 expands to 6, 6, 6, 3, 3, 3. The element-wise product is calculated by multiplying corresponding elements, giving us 6, 6, 6, 6, 6, 6. Then, we re-encode the result back into run-length format, which is 6, 3, 6, 3. This is the output, and it maintains the same compressed structure as the input arrays. Let's look at another example. Here, encoded 1 is 1, 1, 2, 1, 3, 1, and encoded 2 is 4, 1, 5, 1, 6, 1. When expanded, encoded 1 becomes 1, 2, 3, and encoded 2 becomes 4, 5, 6. The element-wise product of these arrays is 4, 10, 18. After re-encoding, the result is 4, 1, 10, 1, 18, 1. This shows that the encoding works even when each value has a frequency of just 1. Now, in the third example, encoded 1 is 1, 5, and encoded 2 is 0, 5. For this example, encoded 1 expands to 1, 1, 1, 1, 1, and encoded 2 expands to 0, 0, 0, 0, 0. The element-wise product is 0, 0, 0, 0, 0, because multiplying any number by 0 results in 0. After re-encoding, we get the result 0, 5. This highlights that the encoding process handles 0 values seamlessly. Now, let's discuss some constraints and edge cases to ensure the solution works correctly under all conditions. One important edge case is when both arrays contain only a single frequency pair, such as encoded 1 equals 2, 1, and encoded 2 equals 3, 1. Here, the output is simply 6, 1, since there's only one product to compute. Another scenario involves arrays of different lengths, where overlapping frequencies must be handled correctly, such as encoded 1 equals 1, 3, 2, 2, and encoded 2 equals 4, 5. In this case, the solution must carefully align the frequencies to compute the correct result. Finally, when one array contains 0 values, the product will also be 0 for those positions, as in the example encoded 1 equals 0, 3, and encoded 2 equals 5, 3, where the output is 0, 3. By addressing these cases, the implementation can ensure robustness and accuracy for any valid input. To begin solving this problem, we can consider the brute force approach. The basic intuition here is to expand both run-length encoded arrays into their full forms. For instance, if one array has elements encoded as _1 is f_1 and _2, f_2, we would expand it into an array where a_1 is repeated f_1 times, followed by a_2 repeated f_2 times. Similarly, the second encoded array would be expanded in the same way. Once both arrays are fully expanded, we can compute the element-wise product by multiplying corresponding elements. After that, the resulting array is encoded back into run-length format. However, this approach comes with trade-offs. Expanding the arrays takes time proportional to the total frequencies of the elements in both arrays, and performing the element-wise multiplication adds further overhead. On top of that, the space complexity can grow significantly for large inputs, as we have to store the fully expanded arrays in memory. While this method is straightforward to implement, it's not efficient for large inputs, making it less suitable for this problem. To address the inefficiencies of the brute force approach, we turn to an optimized solution using the two-pointer technique. Here, instead of expanding the arrays, we process them directly in their encoded form. The key idea is to use two pointers to traverse the segments of the encoded arrays. At each step, we compare the frequencies of the current segments and compute the product of their values. We then determine the number of elements to include in the result based on the smaller frequency. This creates a new segment for the result, consisting of the product of the values and the minimum frequency. After this, we decrement the frequencies of the processed segments by the minimum frequency and move the pointer for any segment whose frequency reaches 0. This process continues until one of the arrays is completely traversed. This method avoids expanding the arrays entirely, making it significantly more efficient. The time complexity is linear, as we only traverse each encoded array once, and the space complexity is minimal, requiring only the output array and a few pointers. This approach is not only faster but also directly produces the result in the desired run-length encoded format, making it both efficient and elegant. The key insight for solving this problem lies in recognizing that we can operate directly on the run-length encoded data without expanding it. The structure of run-length encoding allows us to process segments incrementally, and the two-pointer technique takes advantage of this by traversing the arrays in linear time. The breakthrough moment comes from realizing that we can compute the product of values and handle frequencies dynamically as we go, avoiding the need for intermediate expansions. This makes the two-pointer technique an ideal choice. It is efficient, scalable, and works directly with the compressed data, avoiding the high memory usage and unnecessary computation of the brute force approach. While the brute force method is simpler to implement, it is impractical for large inputs due to its space complexity. On the other hand, the two-pointer technique is slightly more complex to implement but offers significant performance benefits, especially for large datasets. It balances time and space efficiency, making it the most optimal strategy for this problem. By directly operating on the encoded data, this approach aligns perfectly with the problem's structure and requirements. In this problem, we need to compute the element-wise product of two run-length encoded arrays efficiently. A run-length encoded array is represented as a sequence of tuples, where each tuple consists of a value and its frequency. For example, the array 5, 3, 2, 2 would expand to 5, 5, 5, 2, 2. However, fully expanding these arrays can be computationally expensive, especially when the frequencies are large. Our goal is to calculate the product array in a compressed form, avoiding full expansion. To achieve this, we initialize pointers I and j to traverse the two encoded arrays, encoded 1 and encoded 2. Additionally, we use variables remaining 1 and remaining 2 to track the frequencies left to process in the current tuples. Finally, we create an empty result list to store the product array in run-length encoded form. This setup allows us to handle the inputs efficiently without unnecessary memory usage. Now, we begin iterating through the two encoded arrays. As long as both pointers I and j are within the bounds of their respective arrays, we extract the current value and frequency from the tuples at these positions. For encoded 1, I, we retrieve val 1 and frequency 1, and similarly for encoded 2, j, we get val 2 and frequency 2. Next, we determine the smaller frequency between the remaining counts of the two tuples, which we call min_frequency. This represents the number of elements that overlap between the current sections of the two arrays. Using these values, we compute their product as val1 * val2. To store this result, we check the result array. If it's empty or the last tuple in the array has a different value, we append a new tuple, product, min_frequency. On the other hand, if the last tuple in the result already has the same value as the product, we simply increment its frequency by min_frequency. This process ensures the output remains in a compressed, run-length encoded format. After updating the result, we need to adjust our pointers and frequency trackers. We subtract min_frequency from both remaining 1 and remaining 2, reducing the count of elements processed from the current tuples. If remaining 1 reaches 0, it means we've completely processed the current tuple in encoded 1, so we move the pointer I to the next tuple and reset remaining 1 to the frequency of the new tuple. Similarly, if remaining 2 becomes 0, we advance the pointer j to the next tuple and encoded 2 and update remaining 2 accordingly. Once either pointer exceeds the length of its array, we terminate the loop, as there are no more elements to process. At this point, the result array contains the run-length encoded representation of the product array, which we then return as the output. There are several key insights in this approach. First, we avoid fully expanding the encoded arrays. By processing the inputs directly in their compressed form, we save significant memory, especially for large arrays with high frequencies. Second, the use of remaining 1 and remaining 2 allows us to efficiently manage partial overlaps between tuples, ensuring that we process only the necessary elements without redundant calculations. Finally, we maintain the compression of the result by appending only when the product value changes. This avoids unnecessary fragmentation and keeps the output compact, adhering to the run-length encoded format. To implement this algorithm, we rely on a few essential data structures. The input arrays, encoded 1 and encoded 2, are lists of tuples that represent the compressed data. The result array is also a list of tuples, storing the product array in a run-length encoded form. Additionally, we use pointers I and j to traverse the two input arrays, along with counters remaining 1 and remaining 2 to track the elements left to process in each tuple. Regarding complexity, the time complexity of this algorithm is O, n plus m, where n and m are the lengths of the two encoded arrays. This is because each tuple is processed exactly once. The space complexity is O, 1, additional space, as no intermediate data structures are created apart from the output array. This makes the algorithm highly efficient for handling large inputs. To bring everything together, let's walk through an example. Consider the input arrays encoded 1 equals 5, 3, 2, 2, and encoded 2 equals 3, 2, 1, 3. We start with I equals 0, j equals 0, remaining 1 equals 3, and remaining 2 equals 2. First, we calculate the product 5 asterisk 3 equals 15 and determine min_frequency equals 2. We append 15, 2 to the result and update remaining 1 equals 1, moving j to the next tuple. Next, we compute 5 asterisk 1 equals 5 with min_frequency equals 1, appending 5, 1 to the result. Now remaining 1 is 0, so we move I forward. We continue this process until all tuples are processed. The final result is 15, 2, 5, 1, 2, 2, which demonstrates how the algorithm efficiently computes the product without fully expanding the input arrays. This Python implementation solves LeetCode problem number 1868, product of two run-length encoded arrays. The function findRLE computes the element-wise product of two run-length encoded arrays without fully expanding them. First, we initialize two pointers, I and j, to traverse through encoded 1 and encoded 2, respectively. We also initialize an empty list result to store the final run-length encoded product array. The algorithm processes the arrays using a while loop that continues until one of the arrays is exhausted. Inside the loop, it extracts the current value, val1 and val2, and frequency, frequency1 and frequency2, from both encoded arrays. The product of the two values is computed, and the minimum frequency between the two is determined. This ensures that we handle only the overlapping segments of the current run lengths. If the last entry and result has the same value as the computed product, we merge the frequencies by adding the minimum frequency to the last entry. Otherwise, we append a new entry, product, min_frequency, to result. The algorithm then decreases the frequencies of the current segments by min_frequency. If a segment is fully processed, its frequency becomes 0, the corresponding pointer, I or j, is increment to move to the next segment. This approach efficiently calculates the product of the two arrays without expanding them, ensuring optimal space and time complexity. The final result contains the run-length encoded product array. Here, we start by importing the necessary packages and defining our class, solution. The main method, findRLE, takes two run-length encoded arrays as input, encoded 1 and encoded 2. We initialize two pointers, I and j, to traverse through these arrays and create an empty list called result to store the final product in run-length encoded form. The while loop ensures we process both arrays as long as neither pointer has reached the end. Inside the loop, we extract the current value and frequency for both arrays using the pointers. For example, val1 and frequency 1 correspond to the value and frequency from encoded 1, while val2 and frequency 2 are their counterparts in encoded 2. We then calculate the product of val1 and val2, which represents the value in the resulting array, and determine the smaller frequency between frequency 1 and frequency 2 since that's the maximum overlap for the current pair of elements. If the last entry in the result list already has the same product value, we simply increase its frequency by the minimum frequency. Otherwise, we add a new entry with the product and the minimum frequency. Afterward, we decrement the frequencies in encoded 1 and encoded 2 by the minimum frequency, as those portions have now been processed. Finally, we check if the frequency in encoded 1 has reached 0, and if so, we increment pointer I to move to the next element in encoded 1. If the frequency in encoded 2 reaches 0, we increment pointer j to move to the next element in encoded 2. The loop continues until we have processed all elements in both arrays. Once the loop ends, the result list contains the run-length encoded representation of the product of the two input arrays. Finally, we return this result list. This implementation efficiently combines the two encoded arrays by leveraging their run-length formats, minimizing the computational overhead of expanding them into full arrays. The logic ensures that we handle overlapping frequencies correctly and merge consecutive segments with the same product to maintain the run-length encoding format. To solve this problem, we process the two run-length encoded arrays step by step, focusing on their respective values and frequencies. Starting with the first example, the input arrays are encoded 1 equals 1, 3, 2, 2, and encoded 2 equals 3, 3, 4, 2. We initialize pointers I and j to 0, and an empty list called result to store our final output. First, we compare the elements at the current positions, encoded 1, 0 equals 1, 3, and encoded 2, 0 equals 3, 3. The values are val1 equals 1 and val2 equals 3, and the frequencies are both 3. We compute the product of the values, which is 1 asterisk 3 equals 3, and find the minimum frequency, which is min 3, 3 equals 3. This gives us the run-length pair, 3, 3, which we add to the result. Next, we update the arrays to reflect the remaining frequencies, setting both frequency 1 and frequency 2 to 0. This moves both pointers, I and j, to the next elements in their respective arrays. We repeat this process for the next pair, encoded 1, 1 equals 2, 2, and encoded 2, 1 equals 4, 2. Here, the product is 2 asterisk 4 equals 8, and the minimum frequency is 2. We add 8, 2 to the result and update the arrays. Since both arrays are now exhausted, we return the result 3, 3, 8, 2. The output of the first example is 3, 3, 8, 2. Now let's consider a second example where the frequencies between the two arrays do not match perfectly. The input arrays are encoded 1 equals 1, 5, and encoded 2 equals 2, 2, 3, 3. Again, we initialize I equals 0, j equals 0, and result equals. Starting with the first pair, encoded 1, 0 equals 1, 5, and encoded 2, 0 equals 2, 2, we compute the product, which is 1 asterisk 2 equals 2, and take the minimum frequency, min 5, 2 equals 2. This produces the run-length pair, 2, 2, that we add to the result. To update the arrays, we decrement the frequency of encoded 1 to 3, while the frequency of encoded 2 becomes 0. This moves pointer j to the next element in encoded 2. Now, we compare the updated encoded 1, 0 equals 1, 3 with encoded 2, 1 equals 3, 3. The values are val1 equals 1 and val2 equals 3, and the frequencies are both 3. For the pair encoded 1, 0 equals 1, 3, and encoded 2, 1 equals 3, 3, we compute the product as 1 asterisk 3 equals 3 and the minimum frequency is min 3, 3 equals 3. This gives us the run-length pair, 3, 3, which we add to the result. Next, we update the arrays by reducing both frequency 1 and frequency 2 to 0, which moves pointers I and j to the next positions. At this point, both arrays are exhausted since I equals 1 and j equals 2, so we return the result, 2, 2, 3, 3. The output of this example is 2, 2, 3, 3. Now, let's look at a third example where consecutive results can be combined. Here, the input arrays are encoded 1 equals 1, 3, 2, 3, and encoded 2 equals 2, 3, 1, 3. We start by initializing I equals 0, j equals 0, and result equals. The first pair to compare is encoded 1, 0, equals 1, 3, and encoded 2, 0, equals 2, 3. The product is 1 asterisk 2 equals 2, and the minimum frequency is min, 3, 3, equals 3. The pair, 2, 3, is added to the result. After updating the arrays, encoded 1, 0, and encoded 2, 0, are exhausted, so we move I and j to the next elements, encoded 1, 1 equals 2, 3, and encoded 2, 1 equals 1, 3. Comparing these, the product is 2 asterisk 1 equals 2, and the minimum frequency is min, 3, 3, equals 3. Instead of adding another separate run length pair, we notice that the product matches the previous result, result-1, 0, equals 2. Thus, we combine them by increasing the frequency of the last pair in the result, updating result-1, 1, equals 3 plus 3 equals 6. Finally, both arrays are exhausted, and we return the result, 2, 6. This demonstrates how consecutive results with the same product can be combined to optimize the output. Here, we analyze the time complexity of the solution. The algorithm processes both input arrays, encoded 1 and encoded 2, using 2 pointers, I and j. These pointers traverse through each array, incrementing based on the remaining frequency of the current run length encoded groups. For each pair of elements, the algorithm performs constant time operations, computing the product of the two values, finding the minimum frequency between the two groups, updating the result list, and decrementing the frequencies. These steps ensure that each element in encoded 1 and encoded 2 is visited exactly once. As a result, the total number of operations is proportional to the sum of the lengths of the two arrays. This gives us a time complexity of O, m plus n, where m is the number of elements in encoded 1 and n is the number of elements in encoded 2. The time complexity of O, m plus n, applies to all cases best, average, and worst. This is because the algorithm always iterates through both arrays linearly, processing each element exactly once. Now, looking at space complexity, the auxiliary space usage is constant, or O1. Variables like I, j, val1, frequency1, val2, and frequency2 occupy a fixed amount of memory. Meanwhile, the space required for the output list, result, depends on the number of distinct product groups generated. In the worst case, a new group may be created for each pair of elements from encoded 1 and encoded 2. This means the space complexity for the result is O, k, where k represents the number of groups in the final output. Combining these, the overall space complexity is O1 for auxiliary space and O, k for the output. When comparing this optimized algorithm to a naive approach, the efficiency becomes apparent. The naive approach would first expand the run length encoded arrays into their full forms. This expansion produces arrays of sizes n1 and n2, where n1 is the total sum of frequencies in encoded 1, and n2 is the total sum of frequencies in encoded 2. After expansion, it would compute the product for each pair of elements, requiring O, n1 plus n2, time. Finally, it would compress the resulting array back into a run length encoded format, which also takes O, n1 plus n2, time. This results in a time complexity of O, n1 plus n2, and a space complexity of O, n1 plus n2, both of which are much worse than the optimized solution. The optimized approach, by directly working with the run length encoded format, avoids this unnecessary expansion and compression. It processes each pair of elements exactly once and performs constant time operations for multiplication, comparison, and appending. As a result, the time complexity remains O, m plus n, and the space complexity is determined by the result size, O, k, making this approach significantly more efficient. When working on this problem, there are a few common mistakes to avoid. First, expanding the run length encoded arrays into their full forms might seem like an intuitive step, but it's highly inefficient. For instance, if you have an array with 10,000 run length groups, expanding these could result in millions of elements, consuming excessive memory and making the process impractical for large inputs. Next, overlooking edge cases is another frequent issue. Situations like empty arrays, arrays with only one group, or cases where the lengths of the arrays don't match can easily lead to errors, such as accessing indices that don't exist or producing incorrect results. Additionally, pointer mismanagement can cause problems. If you increment pointers incorrectly while traversing the arrays, you might skip over elements or process the same elements multiple times, ultimately leading to wrong outputs. Paying close attention to these details is crucial for success. Another pitfall to watch out for is overcomplicating the problem. It's easy to get caught up in trying to use advanced data structures or sophisticated algorithms, but these often add unnecessary complexity and increase the chances of introducing bugs. A well-implemented two-pointer approach is both simpler and more efficient, so there's no need to look beyond it. Also, never assume that the input is always valid. For example, run lengths should always be positive, but not verifying this could lead to logical errors or even infinite loops in your solution. Properly validating the input at the start can save you from debugging headaches later. By keeping the solution simple and robust, you can avoid these common stumbling blocks. This problem is a great example of how interviewers test your ability to recognize patterns and optimize solutions. Rather than performing unnecessary computations, such as expanding the arrays, the key is to process the inputs directly using the two-pointer technique. Mastering this approach is valuable, as it's widely applicable to problems involving sorted or compressed data. During an interview, you should be ready to explain why the two-pointer method is optimal. It achieves a time complexity of O n plus m, which is far better than the O n asterisk m complexity of the brute force approach, where n and m represent the expanded sizes. Additionally, always account for edge cases like empty arrays or minimal inputs, and be prepared to explain how you handle them. Highlighting the space efficiency of the two-pointer technique, which operates in O(1) extra space, can further demonstrate your understanding of the trade-offs involved. To deepen your understanding, consider related problems that explore similar concepts. For instance, LeetCode 1868, the product of two run-length encoded arrays, is a direct variation of this problem. Solving it thoroughly will prepare you for other scenarios involving compressed data. LeetCode 89, gray code, focuses on bit manipulation but also requires efficient handling of encoded data. Another useful problem is LeetCode 76, minimum window substring, which challenges you to apply the two-pointer technique in the context of string manipulation. Lastly, LeetCode 986, interval list intersections, utilizes a similar two-pointer approach for processing intervals. Working through these problems will help you become more comfortable with the patterns and techniques commonly used in this domain. When considering alternative approaches to this problem, it's important to weigh their trade-offs. The brute force approach involves fully expanding the arrays and then performing element-wise operations. While this method is conceptually simple, it's impractical because of its high time and space complexity, especially for large inputs. The two-pointer approach, on the other hand, is optimal. By iterating through the run length groups directly, it achieves a time complexity of O n plus m and operates with O(1) extra space. While slightly more complex to implement due to pointer management, its efficiency makes it the best choice. Another possible method involves using a hash map to store run lengths as indices for one array and then iterating through the other. This can be useful in certain variations of the problem but introduces additional space overhead, making it less suitable for this specific scenario. Each approach has its merits, but the two-pointer technique strikes the best balance of simplicity and efficiency for this problem. Great work! To wrap up, we explored the problem of multiplying two run-length encoded arrays and reviewed key strategies and takeaways. This problem emphasizes the importance of working with compressed data efficiently. Thank you for joining. Don't forget to like and subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!